Welcome everyone to this webinar about secure and reliability connectivity in LoRaWAN. This webinar is hosted by Semtech, Actility, and the Things Industries. My name is Johan Stokking and I'm the moderator of today. If you have any questions, please ask your question through the Q&A. And at the end of this webinar, I'll give the presenters the opportunity to answer your questions. First, I want to go over the agenda, and I'm going to introduce the speakers. Today, we're talking about one of the most important topics in LoRaWAN, or Internet of Things in general, and that is security. For those new to LoRaWAN, I'll briefly cover what LoRaWAN is and what its unique benefits are. Then Olivier will dive in the protocol fundamentals, and Alper will explain how to implement LoRaWAN securely in practice. And at the end, we have the Q&A. So Alper is Senior Director of Standards and Advanced Technology Development at Actility. And we have Olivier, who is Technical Fellow Wireless IP at Semtech. And Alper and Olivier are also the Chair and Vice Chair of the Technical Committee of the LoRa Alliance. And the Technical Committee is governing the LoRaWAN standards. My name is Johan Stokking. I am CTO and co-founder of the Things Industries and the Things Network. And I am also the chair of the security working group of the LoRa Alliance. And in that role also oversee the security related matters. Yeah, now Internet of Things is connecting things to the internet, as you know, and you can do that in many different ways. There's no single wireless technology that addresses all use cases perfectly. So your phone, for example, is full of wireless technologies, and that's all for different purposes. And it's really the same in connecting things to the internet. So LoRaWAN is designed for a particular class of Internet of Things, and that is filling the gap for long-range, low-power connectivity for use cases that need little bandwidth and long battery life. So this is typically for sending telemetry a few times per day, like environmental sensing, asset tracking, and metering. LoRa is bidirectional, so you can also send messages to the devices and, for example, do firmware updates. LoRaWAN is a messaging protocol on top of LoRa. So LoRaWAN defines really what is in the messages and how the communication works between end devices and the network. And LoRaWAN is a standard with an ecosystem of device makers, gateway makers, network server vendors, operators, and integrators. The LoRaWAN specification is governed by the LoRa Alliance, which was founded 5 years ago. And in the last 5 years, LoRaWAN has been adopted by a wide variety of companies all around the world across many, many different industries. So yeah, that's become really big. So that's introduction of LoRaWAN, and LoRaWAN is a protocol, right? So with any protocol, you should follow the best practices and guidelines when implementing it. So over the past 5 years, we, implementing the LoRaWAN specification, and Alper and Olivier, we all identified several bad practices when implementing LoRaWAN. And these bad practices lead to end devices or connectivity services that are not secure, even though the protocol itself provides all the means to implement solutions securely. So implementation matters. In fact, if you read blog posts or see presentations claiming that LoRaWAN is not secure, that's really about implementing LoRaWAN in an insecure way. So in this webinar, you'll learn that LoRaWAN security is based on proven industrial standards, and you'll also learn how to implement LoRaWAN securely. Now, most of the common best practices are to use the same root key for multiple end devices. It's the same as using the same password for multiple online services, using the ABP instead of the over-the-air activation. You'll learn later in the webinar what the difference is. Another common bad practice that we see is reusing nonces. Those are numbers to be used once, and the whole security fundamentals on LoRaWAN rely on not reusing numbers, and that requires devices to persist those numbers in memory, even when they power cycle. And finally, we see that root keys are often not communicated in a secure way from device makers to distributors to device owners, for example, via email attachments, QR codes with the root keys in there, or even printing root keys on invoices. So those are some of the bad practices. So what do we do? So fortunately, you don't have to implement LoRaWAN yourself. LoRa Alliance has over 500 members that are doing all the groundwork for you. So my company, for example, the Things Industries, is all about implementing LoRaWAN securely in the cloud. We run the biggest LoRaWAN developer community and community network called the Things Network. We have an open source stack, and that gives developers a full transparency of how we implement security, but it also gives them a safe and secure environment, like a sandbox, to test their applications. And yeah, system integrators use our enterprise stack for their mission critical private networks that could be in the cloud, operated by us. We also have customers that manage and operate our product themselves in a private cloud or on premises, depending also on their data security requirements. And finally, device makers can buy pre-provisioned secure elements, and you'll also learn later what that is. And they are already pre-provisioned on a joint server, the Things Industries joint server. So let's dive in the LoRaWAN protocol and how security is integrated in every layer of the protocol. And so first, Olivier will introduce the LoRaWAN protocol security, and then Alper will present implementing LoRaWAN securely. Again, please, if you have any questions, use the Zoom's Q&A feature. At the end of the webinar, we expect to have around 10-15 minutes. I will repeat the questions to the presenters, and you'll get your questions answered. If we don't have time to answer your questions, we'll gather all the questions and we'll make sure that we answer them after the webinar. So, Olivier, please take it from here.
Thank you, Johan. Thanks everybody for joining. So as Johan said, I'm going to deep dive a little bit into the technical details of LoRaWAN protocol security. So here is the schematic of how a network is organized. And as far as security is concerned, and as far as the protocol is concerned, LoRaWAN is describing the communication between an end device and a network. There are gateways in the middle, forwarding and receiving packets, but from the protocol point of view, the gateways are transparent. The end device does not know which gateway it's talking to. The end device is talking to a network server for network optimization, and there we have authentication and integrity of all frames, and MAC commands, medium access control commands, encryption. The end device also talks to an application server where the useful data of the sensor is used. And from time to time, and especially at the beginning of its access to the network, the end device talks to a joint server, which is responsible for establishing a security session. So from the end device to the network server, we have authentication and integrity and some encryption of MAC commands. And from the end device to the application server, we have end-to-end encryption. And the joint server is responsible for establishing a security session. Implementing correctly the LoRaWAN protocol is important, but what is also very important, and which is not part of the specification, is to implement secured IP links between all the network's elements and the gateways. Then, now I'm going to detail all this, what happens with the network server, the joint server, and the application server. So we are basically using, as a security primitive, symmetric cryptography. This choice has been made because symmetric cryptography offers lower payload overhead, so shorter messages, which is very important for low power and low cost devices. There are three families of threats when security is concerned that we need to protect against. So the first one is the unauthorized access. We want to be sure that only the authorized devices can access the network. So this is again the responsibility of the joint server, and the security primitive and procedure we have defined in LoRaWAN is called the joint procedure. The joint procedure is using AES-128, either in CMAC, cipher-based message authentication code, or ECB and ECB, electronic code book mode, to perform the procedure. And this is to offer mutual endpoint authentication between the end device and the network overall, so between the end device and the joint server. Then another set of threats are modification of the data and spoofing of the data. So to prevent modification of data, so to offer integrity protection, we have defined a message integrity check, so a so-called MIC. So a message integrity check ensures, thanks to a key and the security relying on AES-128 CMAC again, that the message is complete, has not been altered. As part of this MIC computation, we are adding a device address, which proves that the device is the origin of the message. And we also add a frame counter, which is a protection against replay protection. So all this protects against modification and spoofing. And this happens between the end device and the network server. So what happens in green is between the end device and the network server. And last, between the end device and the application server, so the entity which is going to use to consume the data of the sensor, to prevent eavesdropping, we apply encryption, and again, we are using a standard AES-128 in counter mode encryption. I'm not going to detail all of this, showing the frame format. On the next slide is the frame authentication and encryption. This is what happens to every single frame in the LoRaWAN protocol. So a frame is composed of some link control, but importantly for security, it has a device address, a frame counter, a message integrity check, and of course, an encrypted payload. So the payload from the end device to the application server is encrypted using AES-128 in CTR mode. And what is important to see is that a session key called AppSkey, application session key, is used for this encryption. Only the application server knows the application key, so only the application server can decrypt. Network session key is used to compute the MIC, the message integrity check. If you change anything to the device address, to the link control, to the frame counter, or to the encrypted payload, then the MIC computation will fail and, well, will not match. And only an entity which has access to the network session key, network S key, can compute and verify the MIC. And this network session key is shared between, the end device and the network server. Message integrity check is 32 bits, which means you have only one chance over 4 billion to have a good MIC when you alter the message. So saying it's really relatively impossible. The session key, AppSkey, and network session key are both 128 bits because, of course, it's AES-128. And they are specific to a device, they are secret, and the device is identified on the network with its address, dev address. A session key, the two session keys are renewed at each session, and the first session starts with device activation. So now I'm going to explain what happens between the end device and the join server, which is the join procedure. So join procedure is a join request followed by the join accept frame. The join procedure is there to make sure that that the end device owns the app key and that the join server also owns the app key. So the join request is signed, is message integrity checked with the app key using AES-128. And what's in there is a join URI, a dev URI, and a dev nonce. The join URI is the address of the join server. Dev URI is the identifier of the device. Both are EUI64-based identifier, which are allocated by the IEEE, so they are global numbers. And dev nonce is a counter to prevent replay attacks. It's also used in key derivation, as we can see in the next slide. So that's the join accept frame. Assuming the previous frame has been accepted by the join server, meaning that the frame is valid, the app key matches, while the MIC matches, therefore the app key matches. That's what the join server is going to answer. It's going to answer with a join nonce, a net ID, a device address, so it's going to allocate the device and address, and some radio settings. All this is protected with a MIC, again computed with the app key, and then it's further encrypted with the same app key. So upon reception, the device will decrypt the message using AppKey, and then verify the message integrity check. If decryption, well, if the message encryption is valid, then it will derive session keys, network session key, and app session key, application session key, using its own key, the app key, the root key, the net ID, and also the join nonce, which it sends in the join request, and the dev nonce, sorry, the join nonce it received in the join accept, and the dev nonce it sends in the join request. Meaning that since those two are counters, each new session derives new session keys. Then I'm going to detail how the app key is stored in the device and in the join server. So this is called device personalization in our LoRaWAN language. This happens after or just during the production of the end device. The end device needs to be provisioned with dev UI. So again, this 64-bit number, join UI, the address of the join server, another 64-bit number, and its secret app key, its secret root key. On the join server side, a list of devices, the join server has to be populated with a list of devices. For each devices, there will be the device EUI, the app key of that device, the secret key of that device, and the home network, meaning which network server is going to be responsible for controlling the device on the network. The join server also needs to be linked securely with IP links to one or several network servers and to one or several application servers. There are several ways to do so, to provision dev UI, join UI, and app key. I think Alper started to explain that just before I rejoined, and he's going to give further details in his presentation how to implement this device personalization and storage of the shared secret keys. On the next slide, it's we discuss here activation by personalization, so-called ABP. So ABP is activation and personalization in a single step. It means you don't need to have a root key, you don't need to have app key, you don't need to talk to a join server. As soon as you start, the device is already connected to a LoRaWAN network and tied to a determined network server, meaning the session key are there, stored in a device, and they will reside here for the entire lifetime of the device. Of course, this session key, network session key, and application session key should be unique, random, and not easily guessable, not easily derived from other fields, because that's the secret, that's the only secret the device is going to hold for its lifetime. So it's more convenient because the device connects immediately to a network, but the drawback is that they cannot renew session, they cannot renew their security session. Therefore, ABP is really reserved for devices for which this security level, so a single session forever, is acceptable. Last, I'm going to talk about what Semtech is doing. So Semtech, of course, is doing a lot for LoRa and LoRaWAN. One of our latest announcements is our LoRa Edge platform. So it's a new transceiver, which we call LR1110, which has LoRa modulation, also Wi-Fi scanning and GNSS scanning for asset management. So it's really a platform for geolocalization. In addition to that, and as far as security is concerned, it brings a lot of simplification for the developers on security, because it includes a cryptographic engine, which basically does everything you need to operate LoRaWAN. So it stores securely root keys, the root key, app key, and the session keys. These session keys are retained over power cycles, the keys cannot be read. You may overwrite keys, but you can never read them. No one can read them, even the device owner. So when you derive a key, so when you derive a session key from app key, you enter the nonces and so on. The session keys are stored in the cryptographic engine, but they are not shown whatsoever. And last, all the AES-128 computation for encryption, decryption, message integrity check, computation or verification are performed, and also the join accept processing. So in one go, the crypto engine is going to decrypt the join accept frame and verify the message integrity check, and it will only give access to the data for the nonce device address if the MIC verification is correct. Last, this transceiver comes with dev EUI and app key already provisioned in the chip. And at the same time they are provisioned in the chip, they are provisioned in Semtech joint server, meaning that you don't have to worry about entering yourself the root key, entering yourself app key, and then communicate it to a joint server. That's done already for you. And you can use Semtech joint server to establish the first session or maybe to establish further sessions. The device owner, of course, doesn't need to use that service. You can override these values and use another joint server, use another service. So that's one example of implementing security on the end device side. So now I leave the floor to Alper, who's in the LoRa Alliance, my boss, because he's the chairman of the technical committee.
Thank you very much, Olivier. So now that we've talked about how we achieved protocol specification security, let's look at how to use it securely to achieve the ultimate goal of reaching secure solutions. First of all, we have to make sure we follow the specs very closely. For example, the OTA versus ABP, we should always prefer OTA whenever it's applicable. The only case where we may have to use an ABP device is when the device is an uplink-only device that cannot support the bidirectional join procedure. Secondly, the implementation should not reset the frame counters unless there's a new session key established through a join procedure. So that means the frame counters shall be retained across power cycles. We see in some poor implementations, the frame counters are reset after power cycling, and that's basically a recipe for a security disaster using the same frame counters. And we have a number of identifiers in our specifications. One to identify the device, that's the dev EUI. Another one is an ephemeral address assigned by the network called dev adder. And FUOTA is the identifier to identify the join server, and the network ID and net ID identifies the network we are using. There are strict rules how these numbers are assigned for dev EUI and FUOTA. These are based on IEEE OUIs. So assigning random dev EUI or FUOTA would confuse the networks, and it would cause at least an operational problem, if not a security problem. And similarly, dev address needs to be assigned based on the net ID assigned to the network. If they are randomly assigned, the operations would have unexpected behavior. So we strongly discourage people from using arbitrarily assigned dev address. And on the net ID side, network should either use a net ID assigned by the LoRa Alliance or should use the shared net ID 0 or 1. In all these respects, we do see some poor implementations out there that are using seemingly random values, and sooner or later they would run into troubles. So let's look at the whole story, how we begin. So the whole story begins by setting an app key on the end device. That setting is done by the device manufacturer. We have to make sure this key is a unique per device. Sharing the same key across multiple devices lead to the so-called domino effect. If any one of the devices are compromised, that leads to the compromise of the other devices as well. That's a very poor practice. Secondly, the keys should be strong, cryptographically strong, meaning they should be hard to guess. Using easy to guess keys like all ones, all zeros, or sequential numbers 0 through 8 repeating itself, or a combination of publicly known values like the dev EUI, app EUI. Again, we encounter such practices, and these are also basically breaking the overall security of the system. On the network side, after the device is initialized with its app key, a join server also needs to have a copy of the same key. Now, the key delivery should be properly secured. If it is shared over a file, the file should be encrypted, ideally by the public key of the join server. And if it is shared through an API, through an interface that runs across the internet, it should have end-to-end integrated protection and privacy by using IPsec or TLS. Again, any compromise in transit would also lead to the compromise of the overall security. And once the keys are in place, they should be securely stored against various attacks. On the end device, it should be practically impossible to extract the keys by unauthorized entities. So any practice like printing the key on the end device, putting it on a sticker, a post-it, or having a device whose key is published in the source code made publicly available, these are somewhat commonly made mistakes we should all avoid. Similarly, the joint server, being the server holding thousands, if not hundreds of thousands of keys, they should be protected against any source of attack from the internet, properly secured behind a firewall with proper access control to prevent unauthorized access. And same thing goes for the device manufacturer. If they have not fully erased the keys, they should also fully secure their infrastructure. So I had already talked about half of the slide in an earlier question. Now, if you would like to have hardware level security on the end device so that the key cannot be easily extracted, that's where secure elements come into the picture. They provide hardware level security for safeguarding the key and all the cryptographic procedures. These are hardware chips that do not export the key once it's burned in, and they provide high-end security for your high-end applications. Similarly, on the joint server side, there's a dedicated hardware equipment, generically called hardware security module. This piece of hardware is both physically protected and also cryptographically protected against various types of attacks. So these two hardware-based solutions can be injected into your solution. You can choose one or the other or both at the same time in order to boost the level of security you have in your end-to-end solution. If we take a step back and look at the network architecture, we see we have gateway, network server, joint server, and application server. These are all infrastructure elements in our architecture. And being part of the overall picture, they should be properly secured using backend infra and communication security. So among themselves, they do communicate with each other over the internet, most of the time using public internet. And that should be properly secured using IPsec and TLS and similar cryptographic solutions. And these infrastructure elements should be behind firewall and have physical security when applicable and have cryptographic security against unauthorized access. Now, another protocol feature we have in LoRa Alliance is firmware update over the air. This feature allows to push a firmware file to a number of devices all at once. It can be used for both pushing firmware and also any large file, be it a configuration file or even application software. So we can talk about this in the context of security from two angles. One is this protocol itself is also properly secured. We mandate the firmware push to the devices have a signed firmware, and the delivery is integrity protected using a multicast group key. And at the end, we use a per device key for integrity protection and verification of the whole procedure. On the other side, FUOTA feature itself is one of the tools we have for providing a full secure solution. So no matter what you do, you will end up having to patch your software, whether it's adding a new feature or fixing bugs. And once the devices are in the field, you would ideally like to do that while the devices are still in the field without having to recall them. And the way to achieve that is by using the FUOTA feature so that you can push software updates and firmware updates to your device over the LoRaWAN connectivity. And that also presents itself as an insurance for any future security bugs you might have in your applications. Through FUOTA, you can patch your applications while they're still in the field. If we take a look at what we basically covered in terms of the protocol security, we have a wireless communication protocol that provides mutual endpoint authentication, data origin authentication, integrity and replay protection, and data encryption, all using AES-128, the state-of-art cryptographic algorithms and keys. On top of that, we provide a FUOTA protocol as an insurance for future issues you might encounter in your application stack. And plus, we are able to inject hardware-level security to the both ends of this communication channel. So that leads us to say we have a secure communication technology. But in order to have an overall solution security, one has to have proper implementation, proper deployment, minding the security considerations as we have talked about in the previous slides. And I'd like to say a few words about the company that I work for, Actility. We're a founding member of LoRa Alliance. We are a core infrastructure vendor serving both tier 1 public operators and also small to large enterprise all around the world. We have a pretty large product portfolio. In our portfolio on the security front, we have a joint server called ThinkPark Activation. It is already integrated with an HSM and several secure elements. It is made available to both active networks and non-active networks through our peering hub, ThinkPark Exchange, which also interconnects the third-party joint servers such as Semtech joint server. And we have a ThinkPark FUOTA, which is our FUOTA server for updating devices in the field. And just to briefly talk about LoRaWAN certification, which is another essential tool we present to the ecosystem. We have a certification program that has a very extensive collection of test cases that covers all aspects of the LoRaWAN specification, including security aspects. We use over 2,000 messages to test the compliance of the devices against LoRaWAN specification. So if you are building a device, we highly recommend you become a member of the LoRa Alliance and get your certification. And if you are deploying networks as an enterprise or public operator, you should seek a LoRaWAN certification on the devices you're using. If you are not already a member, another very strong recommendation is to join the LoRa Alliance. LoRa Alliance is in charge of standardizing the LoRaWAN protocols and also creating and nurturing the ecosystem around that. By becoming a member, you will have access to a large and growing and vibrant ecosystem, and you will also have a chance to participate in the LoRaWAN specification creation and also the marketing activities. If you would like to inquire more, please do get in touch with Derek Wallace, the VP of Marketing in LoRa Alliance. And to celebrate the 5th anniversary of LoRa Alliance, we are organizing a very large event in June in Paris. That's going to feature numerous talks from influential members of the LoRa Alliance and the IoT ecosystem, and there'll be workshops and very informative seminars. Please visit the LoRa Alliance website for registration.
All right.
And with that
presentation,
yes,
thank you very much, Olivier and Alper, for your presentations. We got a bunch of questions in the meantime. We've already been answering them via the chat, if that was possible. Let's go to some of the questions that I would like to answer live. Olivier, this one is for you. It's a question from Islam Sharif. What is the overhead of the joint procedure? So how much overhead is there for security in LoRaWAN?
For security overall, so first of all, each LoRaWAN frame has an override for the protocol, so including security, but also some messaging of the protocol of only 13 bytes. So if you want to know the length of a message, you take your payload, you add 13 bytes, and that's for each message, and that gives you the total overhead. So that's relatively small. In the overhead, of course, you have the address of the device. You need to identify the device. You have the message integrity check, and you have a few message type and so on. So overall, this is 13 bytes. The join request and join accept frames are also themselves a few bytes, maybe 10, 20 bytes. But
that is only one.
Very rare. So that, yeah, there's only one at a time. So you're not supposed to join every day. It's a rare event.
Alper,
13 bytes per frame is the answer.
Alper, when deploying smart meters, and I guess a bunch of your customers are doing that, what would you recommend, OTA or ABP?
Well, definitely OTA for its stronger security, its ability to set up session keys and be able to refresh them. So unless you have an uplink only device, we would always strongly recommend using OTA.
Right. So then a question from Jason George that is about this slide. Question is the join server, is that a separate entity or is it part of the network server? And another related question is that from Siddhant Patel is if you want to develop your own join server, how do you do that? Are there any interfaces?
Great. Okay. So even though we're depicting here the full-blown architecture where every entity is separate, you can combine any of these entities together. You could even put the gateway, network server, and join server and application server together, or have various any other combinations. So yes, you can combine network server and join server. You can have them separately. And the interface between the network server and join server are already standardized by the LoRa Alliance technical committee. You can download the specs that are freely available from the resource hub on the LoRa Alliance website. And following that standard interface, you can build your own join server. You just need to make sure the app EUI you use on your join server should be based on IEEE OUI assignments that you own, not just someone else's OUI. If you follow this, then you can have your own join server and you can deploy your own devices pointing to your join server.
Right. So I think that also answers Dimitri's question. He asked if I own the app key of my devices, is that not insecure to share that with a join server? But you already said that you can actually operate your own join server, right? If you implement the interfaces correctly. So
exactly.
Yeah, so you can really keep that security in your own domain and control. Alper, I got a question about LoRaWAN 1.1 and the different versions. Can you briefly, on the timeline, explain what the LoRaWAN versions are that are available today and what we have just released as part of the LoRa Alliance?
Sure. Today we have both 1.1 and 1.03 released. So what we recommend to the industry is to go with what already has a certification, which is 1.03. So if you're implementing an end device, we recommend you to use 1.0.3 that comes with certification and also open source implementation. And pretty soon, within 2 or 3 months, we will be publishing 1.0.4. That will also come with certification. That's again what will be the version we'll be recommending. And after 1.04, we will come back to LoRaWAN 1.1 specification and complete its certification. And then we'll announce to the community that now it's ready for productization. So for today, it's 1.03. In the near future, in 2 or 3 months, once the 1.04 is public, then it will be 1.04. And probably towards the end of the year, it will be 1.1.
All right, then a question from Tenra Lara-san. He asked, how much do you pay for LoRaWAN certification?
If you're a member, you have access to a pre-certification tool, which will allow you to check that your device meets the spec. Therefore, you will only have to pay once for that device certification. You will be ensured that certification will be met, but the exact pricing of certification is not up to the LoRaWAN Alliance to decide. It's up to the test houses. So I think you should go to them to ask.
Yeah. Olivier, about the DEFNONs. So you explained also that is a number that you should use only once, but we only have 32 bytes of the DEFNONs. So that's here. What if you're out of numbers?
Well, this should not happen. If this happens, you can still change the app key, but normally this should not happen because you're supposed to join every time you lose a network.
Can I jump in here?
Yes.
Yeah. So the DEFNONs, I mean, it's as a 2-octet value, it can run up to like 65,000. Now, due to the ISM limitations, devices cannot have rapid join procedures. So hitting 65,000 joins in the lifetime of a device is unlikely. Nevertheless, it's not impossible. As such, in our specifications, what we recommend is if if the device has any chance of using up all 65,000 dev nonces, then it should have another join EUI to roll over to. So dev nonce space is managed per join EUI dev UI pair by rolling over to another, FEUI dev UI pair. By rolling over to another FEUI dev UI pair, the device can start from zero again.
One question is from Judop Hervé about the gateway. What is the role of the gateway in a secure setup related to LoRaWAN, and how to secure the gateway part? Because gateways are also deployed everywhere and on poles and outside. So can you explain the security aspect here?
Sure. From LoRaWAN security perspective, the LoRaWAN radio gateway does not play any role. All of the cryptographic procedures are run end-to-end between the end device and the network server. As such, the gateway does not play any role at the LoRaWAN layer. So a compromise of a LoRaWAN gateway would not lead to compromise of a LoRaWAN session. Nevertheless, obviously, in order to prevent any service disruption, the LoRaWAN gateway platform should be properly secured against any denial of service attack or any unauthorized access, because failing to do so can be used to take the gateway offline, and that can interrupt the traffic. But other than that, compromise of a gateway would not lead to any cryptographic compromise of the LoRaWAN session.
Great. Alper, about protecting flash, can you explain that? In devices that have their software and maybe also their security keys, how do we protect that?
Right. So when implementing LoRaWAN devices, the device has a key called app key. That's a root key or a master key. So now that needs to be well protected against any adversaries extracting that key, because if that key is extracted, anyone can impersonate the device and steal the session or steal the persona of the end device. So for high-end applications that require super strong security, we advise people to use hardware-based solutions for safeguarding the key and the associated procedures. And these are called secure elements. These are special purpose-built chips that store and process the cryptographic keys and run the procedures. And there is no practical way to extract the keys out of them. And that's the way to go if you're running a high-end use case such as metering, where there's a monetary asset, there's a value involved, and that's subject to various attacks. So yeah, that's how what we recommend people to use hardware-based solutions. It comes at an additional cost, but in cases where the asset is a high-value asset or the application is a high-value application, the additional cost is justified.
Let's see, we have more questions about the lifetime of a session. So how long should a device keep the OTA session active? And also, are there periodic rejoins required? What is your advice, Alper?
As long as the device does not run out of frame counters, which are 32 bits, so it's really not practical to run out of them, the device can maintain its ongoing session. So there can be times the device loses connectivity, not being able to receive downlinks or receive acknowledgements to its uplinks. That's when the application logic will have a backoff procedure, and eventually it may trigger a new join that will trigger a new session. And yeah, these are basically the conditions where a new join, a new session needs to be established.
Right. So regarding the LoRaWAN versions, right? So there are different versions, and you mentioned FUOTA. Alper, can devices, if there is a new LoRaWAN version, like in a few weeks or maybe next year, or LoRaWAN 1.1.1, if you have FUOTA, you can also upgrade your LoRaWAN version on the end device, right?
Exactly, yes. So we made sure the FUOTA feature runs on every version of LoRaWAN layer 2 specification. Through that, you can upgrade any LoRaWAN stack to any other using the application-based FUOTA protocol.
Yeah. So we got a few questions about this really exciting module. first, what is GNSS? And second, how does this work, the geolocation?
Okay, so GNSS is basically GPS, so it's navigation from satellites, global navigation from satellite systems. So how does it work? It's a scanner, meaning that it only listens to the satellites and it sends so-called pseudo ranges to a server which is going to compute the location. So the device itself is not capable of determining its own position, but that's not a problem, because usually that's not what you want to do. What you want to do is the network, the application, to know where the device is. So a dedicated service will take care of that from scans of the of GPS receptions from different satellites. It will compute the location. The same applies to Wi-Fi scanning. So the chip is not going to decode completely Wi-Fi communication. It's going to look for Wi-Fi SSID and report this to the server. And like you would do with Google, look up the position from the list of Wi-Fi access points which are in range.
Yeah. Then another question on this module is, do you need to use the Semtech joint server if you want to use this device?
No, not at all. That's I want to make it crystal clear. You don't have to. The device comes provisioned with dev UI and app key, and you can completely replace that and use whatever service you want.
Right. Last question. We have Alper for the LoRaWAN versions. Can you explain what is the availability of the specification, and is it free to upgrade to a higher LoRaWAN version, or is the specification sort of commercially licensed?
Great. Okay. So we are a very open alliance. We publish our specifications on the internet. Anyone can download them and implement them. They're also open source implementations. So there is no licensing in terms of using our specifications. They can be freely accessed. You just need to go to the resource hub on the LoRaAlliance.org webpage, and you can access not only our specifications, but also a bunch of white papers and informative presentations as well.
Great. So that went really fast. Thank you very much, everyone, for attending this webinar. It's hosted by Semtech Actility and the Things Industries. Again, the LoRaWAN World Expo scheduled for June this year. It's also most important thing is to stay safe and healthy. So also please see this note that the LoRa Alliance will keep you informed as any updates arise, potentially on rescheduling this event. But please keep an eye on this event because it's going to happen and it's going to be great. Thank you very much, and hope to see you soon in another webinar. Thank you.